Hello, good morning in the US and good morning in Canada. Good afternoon in Europe and the Middle East and good evening in Asia. This is the second day of ISCA. I'm Lieven Eekhout from Ghent University and I'm serving as the program chair for this conference. And it's my great pleasure and honor to introduce our second distinguished keynote speaker today, which is Valeria Bertacco from the University of Michigan. Her research interests are in the area of computer design, with specific emphasis on specialized architecture solutions and design viability, including reliability, validation, and hardware security. Valeria is the director of the Applications Driving Architectures Research Center, a prestigious and ambitious center that looks far ahead towards specialized heterogeneous systems with innovations across the system stack, from domain-specific language abstractions down to silicon devices. The ADA Center includes 21 faculty members and 130 students from 10 academic institutions in the US. I guess you will all agree with me that this avenue of research is an extremely important and promising one as we move towards the golden age of computer architecture. Valeria has served as a program chair for the Design Automation Conference, and she has received numerous awards, including being recognized as an ACM Distinguished Scientist and an IEEE Fellow. Now, before giving the floor to Valeria, I would like to remind you all as in the audience to post questions and vote up questions through the Zoom interface. So with this, Valeria, please go ahead.
Thank you, Lieven. And thank you everyone for having me at the very first worldwide ISCA. I must say that I'm sorry that I cannot see you all and I cannot have casual conversation with you, but I do appreciate the unique opportunity of delivering this keynote in my genes. So the third thing I would like to do is to give a special welcome to first-time ISCA participants and new students. I will start by providing them with a 1-minute review of how computer architecture has evolved. In the early days, computer architects' focus was to design faster, better, and lower power general purpose processors. This plot shows how a wide range of processor metrics have evolved over the decades. You can see how around 2005, the NASCALE ended. Prior to that time, one could shrink the size of a transistor while maintaining power density constant. After 2005, leakage issue made it so that was no longer possible, and we no longer were able to scale frequency and power together. More recently, traditional Moore's scaling of CMOS transistor has also drastically slowed down. The plot shows how new products by just one semiconductor company have been manufactured at smaller and smaller technology nodes over the decades, and how in the past few years, this trend has been flattening. And with that, the ability to pack always more and better function in a chip at a very fast pace. So in the past few years, computer architects are resolved to specialize computation. Instead of relying on a large number of generic processors, we've been moving towards a heterogeneous computing system, packing a range of specialized processors in a single chip. As an example, the A12 by Apple includes a GPU, a neural engine, and a range of processor cores. But if our future is made of computing system comprising complex software and a rich set of specialized hardware units, which in turn pack reusable accelerator along with processor cores in a single chip, who will be designing all these different processors in all these different computing systems? To answer this question, let's look at the engineering population who can devote itself to this task. Based on the Bureau of Labor Statistics, in 2010, the US had about 880,000 individuals employed as software developers. The value has increased by 60% in the past decade and is bound to double by 2028. Then we have the software validation engineers. I have to be honest, the Bureau calls them computer programmers, but the job description is really that of software testing. The number of positions for the type of work has been decreasing over the past decade, but it is still a pretty substantial 200,000 people employed in that job just in the United States. And personally, I really consider both these groups together as a software designer, the people who take care of designing software for our complex systems. Finally, we have the blue people. Those are the engineers who design hardware, the architects, the VLSI designer, the people specializing in place and route, time enclosure, and clock tree design. Those make up a few well-funded, talented group. The numbers here are too small so that for you to detect trends. So I'm going to blow them up for you. And here are our computer hardware engineers. A pretty fixed amount, at least for employment in the United States, is 68,000 individuals. That group of people has not changed much since 2010. Yet, we are no longer asking them to improve branch predictors, design a better cache. They are to design a myriad of new complex systems based on a rich family of accelerator components. It doesn't seem feasible, does it? But why is that the software engineering population keeps growing while the hardware one is fixed? And the other question I would like to consider is that of innovation. Innovation blooms when many diverse individuals can contribute to creative idea to an effort. By just looking at this plot, it is not surprising that today we see much faster innovation in the software industry than in the hardware development business. So why is this all happening? As we ask, why is that the hardware designers are in a pretty fixed number over 2 decades here? Well, the first one, I believe, is the cost of doing hardware design. As the cost of designing manufacturing hardware keeps increasing, fewer and fewer new companies can enter the hardware industry, creating basically a very high barrier to entrance. If you have a startup whose product is a silicon chip, you need to raise several $1 million and be able to work for a few years before you can bring your very first product to market. When I was completing my PhD studies, my advisor, Kunle Olukotun, had just started a hardware companies. And as we went our parted ways, he told me, remind me not to do a hardware startup ever again. I think he forgot because he's back at it again. So let me just show a couple of symptoms of these cost trends. This plot reports the startup cost of setting up a new fab for a new leading edge silicon technology node, from 130 nanometer down to the most recent leading edge nodes, 7 and 5. As you can see from the plot, back in 2002, when the leading edge was 130 nanometer, a new fab would cost about $1.5 billion. And at that ticket price, there were 25 companies producing silicon at that node. Every time a new technology showed up, the cost of creating a fab that was able to produce silicon at that technology node went up. And with that, the number of market players shrank. Today, we have no more than 3 companies who can manufacture leading edge silicon because of the huge initial cost. We're talking over $10 billion. And I have to say, along with pretty unsurmountable technical challenges. So it does not surprise that the new small company would have to raise very high investment to be able to manufacture a chip with such high NREs. Not only manufacturing costs are out of control, design costs have followed suit. With smaller nodes come more complex chips, which entail high hardware design effort, more software design, and also increase in mass costs. A new computing system design that is developed from scratch at the 10 nanometer scale is estimated to cost a whopping $180 million today. An amount which also poses a very high barrier to entrance for new companies, and is also prohibited for anything but very large volume products. Just to put things in perspective for a second, consider that the teeny red sliver at the top of the 10 nanometer design effort. That drawing is not to scale. It represents $300,000. And that amount is my overestimate of the cost of developing Slack first product, a company that last year made $400 million in revenue. I guess now they would be in a position to develop a new chip too. The second reason, which I believe is hampering the ability of growing the hardware industry and employment and the contribution to innovation to the hardware design effort, is complexity. All EDA and VLSI people have grown up looking at charts like this. I'm one of them. They were very common up until 10 years ago. The chart shows that an engineer's ability to do good with a transistor available that they could tape out in a chip lags the pace of growth in the number of transistor that can be actually well designed. This picture is usually used as a call to arms for EDA researchers. That is, if we build better tools, engineers will be able to build better chips that will leverage all the resources available to them. Today, that is still true, but it's no longer the critical challenge. The critical challenge is that design complexity got us so entangled that it's difficult to be creative, while also trying to navigate the immense challenges entailed by the sheer size of modern design, and also trying to limit the number of bugs that we leave behind in these designs. This recent study is from 2018, analyzed the size of the mean engineering team at the peak time of development for a hardware project. We can note how both the design teams and the verification team have significantly grown over the prior decade, from 2007 to 2018. A clear indication that complexity has been dramatically increasing, requiring many more people involved in the same project. And with that comes the challenges of managing the whole project effectively. This other recent study was carried out by 2 students at Harvard. Actually, one of them is now a faculty member at Berkeley. And the students have been tracking the number of components that are included in Apple SoC chips since the A4 was first produced in 2010. They would basically take a die shot and analyze the picture in detail to identify every single component. And even here, you can see a very steady growth, which doesn't seem to have grown particularly much in the very last A12, but that could be possibly due to either to complexity limitation or also the fact that the A12 includes a neural engine that may have absorbed many other components in its logic. So where are we today? Well, this is how we design systems today. And this is why the problems that I describe are present. Architects get together and develop schematic of a new accelerator component or a heterogeneous system. And then VLSI and backend engineers translate that architecture into silicon or map it to FPGA or to simulation if it's a very early stage evaluation. Separately from all this work, software developers write software to implement the applications that have to be running on this system. That software is usually compiled in C, C++, assembly. Very rarely, the compiler that translates those languages into a low-level C, C++ or assembly can take advantage of accelerators that the architects have developed on the other side. It is mostly unaware of what is available on the hardware side. So if we want to actually make use of our accelerators, we need someone to manually analyze the code that we generated and refactor it to take advantage of whatever execution can be run on the accelerators. So while the software development is a pretty mature process, the hardware development is also a pretty mature process, the middle layer of translation is definitely very far away from that. And by the way, let's not forget that this entire effort is surrounded by a very thorough simulation, verification, prototyping work to get everything to work together. Now, let's go back for a second to our software developers and hardware designer as reported by the Bureau of Labor Statistics. You can see a mismatch between the vast number of software developers and the small number of hardware engineers. While this worked well, while we were all working on creating better and faster CPU, a few hardware designers could serve a vast population of software applications because our work was independent and separate from the software development. But if we were to accelerate application, we need to know what application those people are writing. And we need to be able to leverage the key needs of that application in developing our accelerator. So that wall basically has to go. So let's summarize where we are at. We talked about 2 challenges that I believe can be solved by one solution. The 2 challenges are the high cost of design and the high design complexity. As a result of these two, we have few hardware designers, and those who are involved in other design has relatively low productivity compared to the past, compared to software development. The thesis of this presentation is that automation is a key to solve both these challenges. Automation of the design process, so to enable the design of new computing system from an application described in a high-level language down to the complete system comprising hardware and software that together compute that application. And we want the hardware to accelerate at least some part of the application who's running the system. If we could achieve that automation, then one, we will be able to increase the size of the population who can develop new computing systems, because we can recruit into the business the software development individual with software development skill, because that's how you specify the application in a high level language. And two, we can also boost design productivity by raising the level of abstraction so that smaller teams can produce new designs. I think both of these efforts would actually improve innovation, one by including more people and more diverse people to the contribution of developing a new compute system, and the other is by letting people spend more time being creative and less time chasing bugs or anything of the like. I have to point out that it's not the first time that automation saved the world. That is, it ignited innovation in computing system designs. Back in the early 70s, silicon integration was booming. Intel had produced its first microprocessor, a 2,300 transistor endeavors, all designed by hand. And when I say by hand, I mean paper and pencil. You can see a portion of the schematic on the left, where you can actually see the transistor laid out on paper. Now, this ability to integrate the transistor into silicon has grown over the decade. And by the late 70s, the effort was unmanageable. People were packing between 30 and 60,000 transistors on a single chip. At that time, one of my colleagues, Lynn Conway, devised a set of simple rules that allowed to simplify and, most importantly, automate the transistor layout process through stick diagrams. And this is a little picture of them, representing the various types of materials to be etched and deposed over the silicon surface. These rules were amenable to automation, meaning they could be translated into a program, and you could develop an algorithm that can explore automating the layout of the transistor on the chip. And that was the beginning of the EDA industry. That's exactly how the EDA industry was born. Now, in 1978, Lynn taught a graduate course at MIT. Oh, I'm sorry, these were some examples of what the EDA had produced in the early days. We start having higher level language and we start having simulation infrastructure. But back to Lynn. So in 1978, she taught a graduate class at MIT on VLSI design, one of the very first class in that space. The students in the class were to use simple hardware design tools. So they weren't the advanced EDA tools we have today, but they were tools that would allow you to specify the various blocks of the design, and then they would automate the plots. And so the students, within a matter of a semester, were producing multiple new silicon designs. And then this process of developing VLSI design through automation was adopted by courses in other United States institutions, and collectively, they train a new generation of engineers, the VLSI designers, that then joined the industry and changed radically the way silicon design was pursued. So we said we need to automate the process of going from applications specified in a high-level language to a system capable of leveraging a heterogeneous hardware accelerator. Coincidentally, this is indeed one of the primary goals of the ADA Center, which I direct, as Lieven pointed out. ADA stands for Application Driving Architectures. And the acronym is also the first name of Ada Lovelace, the very first software programmer back in the 1800s. Ada developed algorithms to program the Babbage machine and a loom. That was one of the constraints of women back in the day. So Ada is a 5-year research endeavor. It started in January 2018. It will end in December 2022. It includes in the research effort 21 faculty members at 9 US institutions, and most of all, there are 130 doctoral and graduate students pursuing all the research. EDA is sponsored by industry and by DARPA, semiconductor companies, all connected together in the context of the SRC consortium. Now, the overarching goal of the center is that of reigniting computing system innovation. Coincidentally, that's exactly what I'm trying to achieve and promote through this talk. Computing system innovation for the 2030 decade. I think we're going to make it up to them with what we have, but we should have some mature processes by then. And EDA proposes to do this through sustained scalability and sustained value creation. This rocket here is our logo. It's propelled by advancing application that will generate demand for new hardware components, and the development of those components with high performance, power, and area will move forward the technology. So we plan to do so by sustained scalability, which in practice means developing new architectures and new technology different from silicon scaling for value creation. So what we want to do on the technology front is we want to embrace technology and devices that are emerging in the research community to evaluate their value at the system level and make them deployable at the system level. The question that we are trying to address in this space is, how can architecture innovation make up for silicon slowdown? How can new devices be systematically integrated in system? How can we eliminate or reduce manufacturing cost barriers? And then we also want to pursue sustained value creation. And that's what we've been discussing so far, creating new design flows that are accessible to a broad engineering community, so to boost participation and in turn boost innovation. What we want to do is develop design flow that enable fast idea to system processing so that people don't drown in those ideas in the management of complexity. And so what we plan to do in that space is how to design the best silicon for a new application. How can a new application domain be enabled at a fast pace? How can system design be democratized? Our work in the center is organized along 3 research vectors: design, architectures, and technology. You're going to see it here. So all the PIs are working on at least 2 areas of this research effort. The little light bulb, the ideal light bulb is the logo for the DEF development effort, which is an effort in enabling these design flows that can take a high level language. I will explain it in a second, but we're talking about domain specific languages, and leverage accelerator to produce efficiently and fairly painlessly complete computing systems. The second theme focuses on developing accelerator, and we want to develop a complete ecosystem or fairly complete ecosystem of accelerator that are flexible and programmable, because by having flexibility and programmability, we can benefit from reuse. So we don't need to call an architect every time somebody wants to develop a new computing system. And the third theme is that of technology-driven system, specifically what I was discussing a minute ago, evaluating which of the emerging technologies benefit which application segment once they're embedded at the system level. We're also exploring the possibility of leveraging primitive in the application level language to indicate what type of devices we would like to have embedded. And while it is not shown in this picture, the data center also has a major effort in developing benchmarks. Benchmarks that are indicative of the type of workloads and the type of application that we will be running 10 years from now, 20 years from now, so that the computer architecture community has something to refer to as a stride to develop the future accelerators. I put there the link of the website where our benchmarks, and actually not just our benchmark, we are also trying to go and dig out from website what are the benchmarks, the architectural benchmarks that are already available in the community, so we don't try to duplicate that effort. But this is the website that is publicly available and just point as a collection of pointers to benchmark suites that are available out there. And so let's move forward to see what is the vision that we have for design flows development. So this is our design flow vision for the 2030 decade. We're exploring that structure right now with the hope that there will be something looking like this, mature and available for software and hardware developer by the early next decade. So in our vision, developers will specify an application using a domain-specific language. For those of you who haven't heard of them, domain-specific languages are high-level programming languages that provide specific primitives to support a given domain. So for instance, Halide is a language that offers a rich set of primitives that enable programmers to implement image transformations very effectively with very little amount of code. And then the compiler takes care of translating those primitives into whatever iterative loops they have to be translated, and find the proper scheduling of the translation so the execution is very efficient. Graphit is a domain-specific language specifically designed to implement graph-based applications. And so there are primitives that will say how to filter a set of vertices from the graph based on a certain criteria, how to traverse a graph going by a set of vertices to the frontier, so going one edge forward, how to apply a certain function to all the vertices in a graph, or maybe to the ones that you filter. So these are all primitives that are very valuable to somebody who's trying to develop graph-based applications, and they allow to express this code very efficiently. Back to our design flow. So we start from application describing domain-specific languages, and then those will be translated into a series of intermediate representations. We realized very early on in the life of the center that you cannot just have one intermediate representation, but indeed it's a rich set. That's because we have a rich research community, but it's also a multi-layer set of intermediate representation, where the first layer is very much DSL facing, and for instance strives to extract concurrency or the control flow, the execution, while the back end is much more looking like a hardware language. It's definitely much more hardware friendly. Then the application is mapped to an accelerator-rich heterogeneous system, which include resources and accelerator dictated by the specific application. So this intermediate representation will figure out which accelerator we want to bring into our heterogeneous system based on what was needed from the initial application that was written. And then from there, we can go into producing a system in package or a prototype FPGA or simulation. As you probably noticed, some DSL seems to show up very late in the design flow process. This is because there are domain-specific languages that are much more hardware-facing, and they're basically specific languages in the domain of H-level synthesis. So there are ways to describe hardware, even if it's more abstracted than traditional hardware description languages. In the past 2 or 3 years, actually since the center started, we have observed a marked increase in the number of domain-specific languages that the researchers have been proposing. This is because they're efficient and enable to write application in a very effective and productive way. And so researchers have been exploring domain-specific languages for a varied range of domains. And so we think very soon there will also start being infrastructure to support the development of new domain-specific languages. So I can go and wake up tomorrow morning and decide I want to do a domain-specific language in a new domain, and I should, or I hope I will, be able to find infrastructure that help me develop the compiler. Maybe there could be template structures, and then do verification among all the transformation I'm trying to do. So this is our complete design flow diagram that we envision in the data center. During the early years of data center, basically the last 2 years, the center has dedicated significant effort to enable this design flow. And we started by proposing or presenting and developing several building blocks of the design flow diagrams. And you can see them here circled in red. Now, don't get me wrong, there are many other DSLs, there are many other accelerators out there. It looks from this diagram like most of it is done in Ada. It's just because I want to highlight the type of work that Ada is doing, but there are many more components in all these stages that are available by the research community. And then after the building blocks started to be available, a number of our researchers have also started to develop some segments within that flow. So for instance, Zach Tatlow at University of Washington has mapped the relay domain-specific language, NIR, to Vita, which is a neural network accelerator that executes on FPGAs. Adrian Sampson at Cornell has developed Dahlia, which is a type-checked high-level synthesis language. Taco and Graphite are two languages, both developed by faculty at MIT. Taco has been developed by Samana Amarasinghe, and Graphite has been developed by Julian Shun. And both of them originally compiled this language to C and C++, but later they had developed compiler targets for GPUs, which I claim is a type of accelerator that is flexible and programmable. And then finally, Chris Button at Cornell has mapped PyMetal to hardware. What are we doing now is striving to work on projects that enable complete design flows, from the DSLs all the way to a complete accelerator-rich heterogeneous system. Our goal is to develop a few complete flows in the next year or two, so that we can demonstrate that the ADA design flow is viable and to evaluate the benefit that it brings in productivity in developing new computing systems. So I'm illustrating here how the project fit in our diagram, and then I will describe them briefly one by one. A first project that, all these projects, by the way, has started in December, January, so they're very recent and they're just new explorations. The first project I will describe is a project to map the tiramisu compiler into a heterogeneous system that includes a natural language processing accelerator. The second is a process of compiling the Graphite domain-specific language into a system that leverages a graph processor accelerator. And then the last one, pursue a complete flow from the relay language, which is part of the TVM framework that has been developed at the University of Washington for neural networks, also into hardware, including a natural language processor accelerator. But in this case, there is a twist where we are pursuing the investigation of another language as an intermediate framework to create a structured translation between the two. So the first complete flow, as I mentioned, is the one from Tiramisu to FlexNLP. Tiramisu is a compiler developed by Samana Amarasinghe and Riyad Baghdadi, both at MIT. Samana Amarasinghe is a faculty member there, and Riyad is a postdoc at MIT. And the compiler optimizes the generation of code for neural networks. It started from a C++ or a PyTorch code, and it leverages polyhedral representation to optimize the code that it designed. So far, the team has been generating targets for x86, for CUDA, and also for FPGAs. On the other end, we have the FlexNLP natural language processing processor developed at Harvard by Gu Wei. And this FlexNLP processor is flexible and programmable, so it can actually run a wide range of NL application, including speech recognition, language translation, even DNA sequence analysis, sentiment classification, and so on. It leverages multiple specialized processing engines and is controlled via AXI command, ARM EXI command. This is actually a very new project that got recently taped out and got back to Gu's hands right before we went into lockdown. So what they plan to do in this process, collaborating together, is first of all to develop an API that the Tiramisu compiler can target and that has function that can be implemented using the FlexNLP commands. And that API will be the interface to be able to automate and modify the compiler to generate a set of primitives that can then be implemented or modified separately. In addition, they are developing a new module for Tiramisu to support automatic copies of data in the FlexNLP processors. The second effort is that of mapping Graphite, DSL, specified applications into an heterogeneous system that includes the Omega accelerator. So Graphite, as you see on the top right side of the picture, is a domain-specific language for graphs that support the specification of graph application. You can see some of the primitives there: from, apply, filter. These are all with relation to a graph. And then the Omega accelerator is a distributed accelerator solution that augments a chip multiprocessor by providing dedicated scratchpad storage for each core and a very simple processing engine. And the way it boosts the performance of running graph application is by storing in the scratchpads those vertices in the graph that are most often accessed. This is because a common trend in graph is that in moving from vertex to vertex, there are very unpredictable patterns of accessing memory. And by using this scratchpad, we can remove from the caches all those frequent access vertices so that they're always available and they don't pollute the caches for other activities like edge traversal. So what we propose to do is to take the Graphite compiler. Usually Graphite is translated to C++ or to CUDA, so to a more general platform, and try to leverage the Omega architecture. One thing I would like to point out is when Graphite is translated to C++, a lot of that domain knowledge that is actually visual in the high-level application is lost. What we obtain is an ocean of C code, and it's actually quite impossible to figure out what's happening in the application. So if somebody were to go and look at the compiled Graphite code and figure out what portion to accelerate and where to accelerate, I think that would be quite a nightmare. But if instead we start from the high-level language, those primitives, the powerful primitives are right there and they're visible and they can be extracted and mapped to the accelerator. So that's exactly what we are proposing to do here. What we want to do is to take a Graphite application and then modify the middle intermediate representation of the Graphite compiler by identifying the primitives that our Omega accelerator can run and extract them, defining them as external functions. So they never get compiled after that. Then separately, we compile the rest of the code and we implement the primitives through Omega commands. So it would be a mix of writing to memory map registers and issuing command to the accelerator. And then the two pieces of code are linked together in the C++ toolchain, and we can run this application right now in a Gem 5 augmented implementation of a CMP with Omega. Now, this is just the first step. Omega can only accelerate some of the Graphite primitives. Our vision for a more general approach to go down this road is to start with one domain-specific language and take some of those primitives that can be executed by an accelerator and run it on that accelerator. And then from there, we would like to be able to leverage multiple accelerators if necessary to run all the primitives in the system. And then finally, an application in general runs on as multiple domains and may need multiple domain-specific languages to be efficiently described. So we would have a set of DSL whose primitives are mapped to a set of accelerators. One thing I would like to point out is that looking at these domain-specific languages is a great guidance in deciding what function to accelerate, because the people who develop the DSL are domain experts and they provide primitive based on the activities that programmers need to run a lot. And by accelerating those, we are bound to get good performance advantage. And in addition, it gives the additional benefit that is much easier to extract a primitive and map that to the accelerator instead of reverse engineering the code and trying to figure out what block should be mapped. I promise I will describe another project. So this is a mapping from the relay domain-specific language to the Flex NLP accelerator, or a heterogeneous system that includes a Flex NLP accelerator. Relay is a domain-specific language to describe deep learning. It's part of the TVM framework that is developed at the University of Washington. But now this translation uses an additional approach. So the idea is to take a low-level intermediate representation of relay code and the list of commands the Flex NLP can execute. And then we use this ILA. That's technology that was developed at Princeton by Sharon Malik. The other contributors are Zach Tatlock from the University of Washington, and again, Gu Wei from Harvard. Gu Wei collaborates a lot also in this project with David Brooks. The ILA, instruction level abstraction, can be used to abstract away the functionality of both the intermediate representation and the Flex NLP accelerator in a very simple and structured format. So we can write an ILA for the relay language, actually the relay intermediate representation, and one ILA for the Flex NLP accelerator, which is the list of commands it can execute in an ILA format. And then from there, what we need to do is to take each instruction of the relay ILA and translate it into a simple program, a program fragment of the Flex NLP ILA. So basically that would be, how do I execute this instruction on that accelerator? And ILA is this intermediate format that helps provide much more structure in this process. And then ILA also provide a number of additional features. For instance, it has infrastructure to be able to verify that each segment is equivalent to the command that I issued. And because it's in small blocks, the complexity is manageable. So we looked at these projects. We look at the design flow diagram. One would ask, all right, now Valeria is allowing all the software engineers to specify computing system. That's great. There's going to be a lot of innovation. But what is the role of an architect in this whole framework? Well, first of all, one of the key efforts of the architects and one of the key components that is needed to be able to do all this is to design a flexible and programmable ecosystem of accelerators. Because if they're not flexible and programmable, they're not reusable. And if they're not reusable, every time we design a new heterogeneous system, we need to start again redesigning the accelerator, which is going to not be scalable and is not going to allow innovation to bloom. In addition, another key effort of the architects is to integrate this accelerator in a complete hardware system. Just because I plop accelerator in a silicon chip, they're not going to all work together. So for instance, one of the early efforts in data center was a project by Sarita Adve at Urbana-Champaign called Spandex, which was defining communication protocol between different accelerators based on their type of memory access activities. So I'm counting heavily on the reusability of these components so that their creation is independent on new design. Basically, I see accelerators as a software library for a developer. These are the type of bricks you have to build the system that you want. And then if you need to write something that doesn't use any of those bricks, then you have to write your own code, and then will run on the CPU. And again, reusability, beside allowing the architects to leverage their effort, it also allows the components to mature so that the amount of effort dedicated to verification is reduced over time. Second, one of the key aspects I think is critical for the architect is to collaborate with compiler and programming languages researcher to create end-to-end system design infrastructure. Right now, it's very hard, and we're noticing this from our first experiences. It's very hard to design a compiler that leverages accelerator unless you have intimate knowledge of that accelerator. And maybe part of this problem is because the accelerator planet is still fairly young. But we noticed that unless the people who develop the accelerator are part of the team, it's very difficult to modify the compiler to leverage that accelerator. And then on the other hand, often the accelerator functionality needs to be modified and adapted in the process of doing this integration, because you realize only when you're trying to compile to that accelerator that some of the primitives are not well aligned with what the compiler, or better, the domain-specific language needs. Usually in traditional initial effort in the accelerator space, architects would simply understand the application domain and implement function in the hardware that were critical, and they there were actually opportunity for acceleration of some portions of that. But once you're trying to align yourself with domain-specific language and compiler, the collaborative effort is really critical. Now, earlier on, if you remember, I had that diagram of the traditional design where we saw all the software developer on one side with a brick wall and then the few hardware designer on the other side. I think in the future, the community will be much more blended with the need, at least, of smaller groups to develop each part of this effort, but groups that are well connected and interact with each other. So ideally, we're not going to have just a computer architecture conference, but it's going to be a computer system conference where people actually work together and interact with each other. And I think that's a critical aspect to be able to make this whole automation effort work together. Now, you're going to say, wait, people grow up, they go to school and they learn to be computer architects, or they learn to be programming language experts, or they learn to be compilers. How are we going to put this all together? Well, by exposing people to each other research field of research. So for instance, one of the efforts that we have been doing as part of the ADA Center is to broaden participation through ADA hackathons. In the center, we have PIs who are compiler experts, we have PIs who are technology experts, and we have PIs who are architecture experts. But what we do is we engage students in hackathons, and we bring them all together, and we expose students who do not work for their PhD research in a certain space to get to know more about that space. So for instance, a couple of years ago, we did a hackathon on mapping software application into FPGAs. And there were students who were compilers people, and they never had to worry about that. They never had to handle hardware. Their target was C and C++. But through the hackathon, they got exposed to the challenges of mapping a port and worrying about a clock cycle, things that they were not made aware of before, and they got to learn a lot in that process. Most recently, last October, Zach Tatlock coordinated a hackathon where all the students participated. It was over 70 students engaged in contributing to development of features of a domain-specific language or a compiler. And they worked together to enhance and add feature to the relay domain-specific language. I have a little video I would like to show you that we generated out of that experience, so you can hear a little bit the voices of the students in this experience.
My name is Zach Hallock, and I'm a faculty member at the University of Washington and an ADA Center PI. Today we're having the Fall 2019 ADA Hackathon, and students are working on 7 different important topics in the TV and relay effort.
My name is Valeria Bertacco, and I'm a student from the University of Michigan. Today we're working on creating a fuzzer for the language relay. So we are randomly generating different relay programs and then running them to validate our compiler.
The way we were splitting up work was to basically do it in a pair programming style, so Max is the one on the keyboard that's typing, and then Emily and I are looking up documentation or reading things from other places, and we should be being like, oh, we should do it this way or that.
The structure of the hackathon is something a little bit new that we haven't done in the past, and this was inspired by feedback from the center director, Valeria, as well as Todd Austin. What we were trying to do this time is give students more open-ended challenges that are highly research relevant to our actual efforts in the ADA Center.
Really fun. We're doing the ADA seminars like this one right here. We get to meet other students, talk about our research together. We get to meet with professors and sponsors.
Overall, I think this hackathon is super useful. Me and the other members of my team started from knowing absolutely nothing about TDM and the Relay IR, and as we're going through, we're gaining all this knowledge and bonding together as a group, and it's super productive, and I really enjoy being part of my team.
So what we try to do with those hackathons is to bring people together so they get to know about each other, research domain, and they can then later on color and drive a community that is across domain aware and can support this type of design flows where architects and programming language experts and compilers really have to have knowledge of each other's field, even if they're not doing each other's job in any way or form. Now, before I wrap up my talk, I realized that early on, I talked about manufacturing cost as a big barrier to entrance for innovation and for new companies. And that is not part of my design flow story. So you may say, Valeria, you can do anything you want with the design flow. Is it manufacturing costs are still through the roof? Ain't gonna solve the problem. Well, while it's not part of this talk, it's also one of the focuses of the Data Research Center. And I truly believe that the way to abate manufacturing costs is to go through this integrated chip design. There's been a significant initial work, I would say, in that space. There are a few companies who are already exploring that. There is an entire DARPA program dedicated to this. And there's been some research also in the Data Research Center about that. This integrated chip design is when the manufacturing is no longer of a monolithic chip, but is rather of chiplets that provide certain function. I mean, it would be fantastic if these chiplets were one-to-one mapping with accelerators. That would make everybody's life very easy. But there are additional constraints where that is not always possible. And the judgment is not clear yet on that space. But the idea is that the people who manufacture would mass produce chiplets, and then a startup would be able to come into the market and simply bond those chiplets on an interposer, package everything together, and they would have their chip produced. One of the efforts in the data center in this space was to produce a flexible interposer, because one of the problems on traditional system in package design is that you have to go and produce a customized interposer for your chip. So we went and tried to develop a flexible interposer that can leverage its bridges or can burn fuses to create the logic that is needed to connect the chiplets the way we want. And we also did some studies on the type of yield that you can obtain by those bonding, with the idea that the bond of chiplets to interposer will be done at the startup company, no longer at the fantastic high-cost manufacturing company. So again, my answer to manufacturing cost is we definitely need to pursue this integrated chip design to be able to manage that and decouple that from the cost of entrance. And then the other question that may arise is, okay, so if the architects are developing all these accelerators that are flexible and programmable and reusable, are they going to be out of business? Because once we have the whole ecosystem developed, people can just package their heterogeneous system, taking the accelerator we want. What do we need architects for? And maybe you're already past that and you're not worrying about that. But I actually believe that the application will keep emerging. New application will keep emerging in the future, which will drive the need for new and new accelerators. So if we just look at the near future with augmented reality, with volumetric displays, machine learning application beyond neural networks, there is a broad range of new application emerging in the community that has a lot of demands, and they will require always new accelerators to be developed. And I hope that through this approach, and thanks to the architects, we will be able to, in the future, accelerate the amount of time that goes from when a new application emerges and it becomes popular to when we have hardware for it. If you think back at how neural network became popular, that was almost a decade ago. And for several years, neural networks were popular, but they were only executed in software. It took, I would say, about 5 years from when the application was popular to when people start having hardware to accelerate that application. And it was a first, but I hope that in the future, we will be able to shrink that amount of time and go from application need to accelerated hardware way faster. Only the architects can make that happen. Another thought that could be emerging is, what if we can use machine learning to generate the accelerators? And I think that's a very far away problem. Accelerators require a lot of understanding of the application domain, require a lot of custom work. If we ever get to that point, I think there will be bigger problems to worry about. So to conclude, I would like to thank, first of all, the ADA students. I have to tell you that about a couple of weeks ago, we had our annual symposium that, of course, this year was held in a virtual space, and we had over 100 participants, sponsors, PIs, and students. And for that occasion, our students developed demos, videos of their demos. So lots of projects that were presented in short videos with 26 demos. And while these demos are now protected by sponsor access, you will see them appearing over time in Twitter or released by the students. And then finally, I would like to thank our sponsors, which I mentioned earlier on, and they are working all together under the auspices of the SRC consortium. Thank you very much, everyone.
Thank you, Valeria, for this excellent talk. It was very enlightening. So I invite the audience to post questions on the Zoom interface. So one question already popped up. So what's your view or depth versus breadth that students should be educated in?
What's my view of what versus what? I cannot understand.
Depth versus the breadth for the students.
Oh, depth versus breadth for students. Yeah. I'm trying to make the case that students don't need to be as deep. Specifically, they don't need to be as deep in the knowledge of the tool and the application of the day. If they know core concepts on algorithm, they become very flexible. But I think there is definitely a need for breadth awareness. And by the way, in our conversation, when we talk about breadth, we talk about computer architects understanding about compilers. That, in the big scheme of things, is minimal breadth.
Right. So one other question that I had was, so you're looking into innovations in software and architecture and hardware, silicon. So where do you think the highest gains are to be obtained in terms of performance and or efficiency along those three components of the system stack?
Well, traditionally, the higher the abstraction level, the more the opportunities, right? So while everything has to fall in the right place, you can kill that opportunity by having a domain-specific language that does not express primitives that then are the vast majority of the execution, for instance, right? So I think, of course, you have to start by having an ideal domain-specific language that can target what's really complex. And by the way, let me clarify something. When people write domain-specific languages, they focus on two aspects. One, providing primitives that require a lot of coding to be specified. And that's not necessarily something that presents itself to a lot of acceleration. It saves a lot of productivity time to the engineer. And the other is in focusing on primitives where code optimization can do a lot. And again, that's not necessarily the case. Then accelerating that gives you a lot of benefit. So it's at the DSL, but you need to have the hardware awareness to create the primitive that then can give you a lot of performance benefit.
Mm-hmm. One other question that comes in is, what's your vision of using machine learning to facilitate the whole DSL IR accelerator pipeline? Maybe not using ML to generate the whole system, but maybe to use in some parts.
So there is actually a project that also started along with completed design flow. So just a few months ago, and I didn't talk about it. And the idea is this. Normally, when you compile, you go from the domain-specific language to the intermediate representation to the hardware. And the researcher, in this case, Adrian Sampson from Cornell and Samara Marasinghe from MIT, are developing the RI, the opposite of an intermediate representation. And the RI goal is to create an abstraction of the hardware functionality so that with machine learning, you can then train the compiler to use the primitives in that abstraction that are most efficient for the execution. So we have started to see a little bit of work on leveraging machine learning in optimizing compiler design. Mm-hmm. You asked me a much bigger question to which I don't really have an answer, but I'm saying it's growing. There are already initial efforts.
Mm-hmm. Maybe one last question before we wrap up and go to the business meeting. So can we think of integrating all the various domain-specific languages and IRs? Oh, my question disappeared. Accelerators to a single platform. So can we come up with a single IR that encompasses all the different application domains?
To be honest with you, the idea of the single IR was my idea when this center started. I was presenting that diagram. There was just one IR, the ADA IR. It died right away. And the reason it died is it's double. First of all, we have a very rich community of researchers here thinking about this problem. They're not going to follow the rules and all go to the same IR. And then that IR doesn't fit my needs. It's a problem, right? I think the only way to make this successful is embrace what's being offered out there and use it with the best, and basically let the best situation win. And so now, and then the other aspect is, originally I was thinking the IR, the golden model, but really it's a multi-stage process, and you need these intermediate IRs to be able to have multiple targets. I see my colleagues are showing up. I think I need to get off the screen. Is that correct?
Yes, we were reaching the hour. So thank you again, Valeria, for this.
Okay, thank you very much. And hello, Giuseppe and Babak and Mohammed and Jose. Bye-bye.